by David Martí-Pete from Liverpool.
Right. Thank you so much. It's great to be here, and I'm happy to finish this series of lectures by the organizers. So today I was thinking what to talk for this survey. So I wanted to give a talk in transcendental dynamics, and Phil already talked about wandering domains. So then looking at the topics of talks that will be in the conference in week 3, I thought it would be helpful to have a small survey about dimensions of Julia sets. There are 2-3 talks, I think, by Bogusha, by Krzysztof, and by Anna as well about dimensions. Right. So how to define the Hausdorff dimension? So here, generally, if you have a set in Rn, for us, n is going to be 2. You can define the S-dimensional Hausdorff measure. So you fix a value of S between 0 and 2 in this case. And then you take your set X and you cover it by some open sets of diameter bounded by delta. So because we are in the UK, a common exercise to do, I think, is to try to estimate the Hausdorff dimension of the boundary of the UK, at least when you go to schools to give talks about fractal dimension. That's what students like to do. Right, so you cover your set X with these balls, and then you compute, I don't know if this has a pointer, you compute this sum here with the exponent S, and then make delta tend to 0. So if S is very small, then this quantity will always be infinity. And if S is close to 2, then this quantity is going to be equal to 0. And there is exactly one value in the middle where there is this jump from being infinity to being 0. And this is the value that gives you, so at the point S where this changes from infinity to 0, this is the value of the Hausdorff dimension of your set. At this particular value of the dimension, the measure can be equal to 0, have a finite value, or be infinity. Right. Okay, so some examples of dimensions of fractal sets. So the Polonian gasket has Hausdorff dimension about 1.3. The Sierpinski carpet about 1.9. And everyone's favorite fractal set, the boundary of the Mandelbrot set, has Hausdorff dimension equal to 2. Right, so there is no one standard value of fractal dimension, so you can define, in addition to the Hausdorff dimension, you can define the box counting dimension. So you cover your set with boxes, and then you count how many of these boxes intersect your set, and then take the limit. So this number here, an epsilon, is the number of boxes of side length epsilon required to cover your set, and then take the limit when epsilon tends to 0. So this limit does not necessarily exist. So usually you have a lower box dimension and an upper box dimension. But when the limit exists, then you define this value to be your box dimension. I should say that the box dimension is only for bounded sets. And then there is the packing dimension. So the packing dimension is very similar to the Hausdorff dimension, but instead of having your set, instead of having like a cover of your set, you now consider balls that have diameter less than delta, but centers in your set. So you need to cover your set. You need to put these balls with center in your set so that they are still disjoint. So you have a disjoint collection of balls with centers in the set of diameter less than delta. And you have this relationship here. So the Hausdorff dimension is the smallest of the 3, then the packing dimension, and then the box dimension. But there are many sets for which these 3 quantities actually coincide. But by making your set looking different, very different at different scales, you can make them be different. So for example, if you have the Cantor set, And instead of removing 1/3 every time, you play with, for example, you remove 1/3 for a long time, and then you remove something smaller for an even longer time, and then you go back to 1/3. You can make the Hausdorff dimension and the packing dimension be different. Any questions about dimensions till here? No? Okay. Right, so this is just an example of how to compute, in this case, the box dimension of the Sierpinski carpet. So as I said, so you need to find, see how many squares you need to cover the set. So if you choose epsilon to be 3 to the minus n, then you need 8 to the n squared. So for example, here n is equal to, for n equals 1, you have, you have 1, 2, 3, 4, 5, 6, 7. You need 8 squares of size 1/3. And then here you would need 8 times 8, etc. So you plug in these quantities, and then you see that the limit actually does not depend on n because they cancel, and you get your value of the box dimension. And in this case, the box dimension equals the Hausdorff dimension. Okay, so in the talk, we're going to be looking at Julia sets of entire functions. These are going to be either polynomials or transcendental entire functions. So we already, I think many people already defined the Fatou set and the Julia set. In addition to this partition, we will also consider the other partition given by whether points escape to infinity. We will say this is I of f is the escaping set, or whether points have a bounded orbit. We will call this k of f. And then if f is a polynomial, these are the two only possibilities. But if f is transcendental, then there is a third case, which is that of unbounded non-escaping orbits. So you have orbits which go arbitrarily close to infinity, but then go back to a bounded part of the plane, etc. So we call this the Bungie set. It was studied first by Dave Sixsmith and John Osborne, and the notation is BU of f. Okay. Right, so for polynomials, we can have that the Hausdorff dimension of the Julia set can be arbitrarily small. So for example, you can think, if you take values of C outside of the Mandelbrot set, the Julia set will be a Cantor set. And then if you make C tend to infinity, you will get these Cantor sets which get more and more sparse as C tends to infinity. So the dimension will tend to 0, but it cannot get to 0. So the Julia set of a polynomial has strictly positive Hausdorff dimension, but you can achieve every value in between. However, for transcendental entire functions, this is not the case. The smallest value you can achieve is 1. So this is because the Julia set always contains some continua. So for example, so this follows from a result of Baker when he was studying multiply connected wandering domains. So he proved that multiply connected wandering domains, they're always bounded, so they contain some continua on the boundary. So you have this situation that either all your Fatou components are bounded, are simply connected, sorry, in which case you have a continua in the Julia set which is unbounded, or if you have one that is multiply connected, then it needs to be bounded. So the outermost boundary will give you some continua in the Julia set and dimension at least 1. Okay? Right. So in going to the other side of the spectrum, what are the largest possible dimensions? So Mitsu has this nice paper where he proves that the dimensions of some Julia sets in the quadratic family can be equal to 2. I think before this paper, people conjectured that it could be arbitrarily close to 2, but he showed that actually 2 is realized for some maps, and he used parabolic implosion to do this. This is the paper where he shows that the dimension of the Mandelbrot set, the boundary of the Mandelbrot set, is equal to 2. Okay, so what about, also, the situation can get even worse in some sense. So you can also have Julia sets of polynomials which have positive Lebesgue measure. Right. So the theme of this is, sorry, let me go back. So for small values of the dimension, it is easy to find polynomials with Julia sets of small Hausdorff dimension. But for transcendental entire functions, you will see that it's much more complicated to get small values of the dimension. On the other hand, these values, large values of the dimension, they are difficult to find for polynomials, right? So either both this construction and this construction are quite technical. However, for transcendental entire functions, this is the easy case. So for transcendental entire functions, high dimensions is the standard in some sense. So of course, one trivial example is when we have that the Julia set is just the whole plane. It has dimension 2, but most other Julia sets, many other Julia sets, which are not the whole plane, still have Hausdorff dimension 2. For example, McMullen has this really nice paper where he proves that in the exponential family, every Julia set has Hausdorff dimension 2. In the same paper, he also looks at other families, such as, so this one here is the sign family, and he shows that for the sign family, you even have more. You have that the Julia set has positive area. But for hyperbolic exponentials, the area of the Julia set is 0. So one way to think about this, maybe it's in terms of which tracks the function has. So if you have the exponential function, the only track is here. And if you have the sign, you have 2 tracks. So roughly speaking, for the exponential function, your Julia set is covering kind of half of the space in the plane, while for the sine function, you have these 2 tracks which are in the upper and the lower half plane. So when you zoom out, most of the space is covered by these 2 tracks. You only have this strip that is outside the tracks. So this shows that this is the argument behind the Julia set of the sine having this positive area. Okay, I should write this down. Right, so these are 2 pictures from McMullen's paper. You can see on the right, the Julia set in the sine family is much more dense than the exponential one. Okay, so what technique did McMullen use to study this? So as Alexandra was saying the other day, for the Hausdorff dimension, it is easier to get upper bounds, and it's usually more complicated to get lower bounds. So to get an upper bound, you just need to have some cover, but the lower bounds, this result of McMullen was really helpful, and many of the papers that followed after used this same technique to compute lower bounds for dimensions of Julia sets. So how does it work? So you start with an initial cover E0 of your Julia set, and then you define successive covers with smaller and smaller diameters given by taking preimages by your map of the starting cover E0. So you start with the cover E0, and then you take preimages of all the sets in this cover, and you get the cover E1, and then you take further preimages, you get E2, etc. And your diameters go to 0. Then you need to find 2 quantities. So you look at the maximum of the diameters of the pieces in the level n, and you want to find an upper bound of these diameters for a given value of n. And then you also need to find the density of the pieces of level n+1 with respect to level n. So you need a lower bound for this density here. And then with these quantities delta n, like little dn and delta n, you plug them in this formula here, and this gives you a lower bound for the dimension. So basically, you're creating this initial cover, taking pre-images, and then estimating what the size and the density of these sets is to get the dimension. Any questions? Yes?
In this formula,
Yeah.
shouldn't we dn go up dn in the denominator rather than di, or does it give the same result?
I thought it was di, but I would need to check. Maybe Gwyneth will know. I mean, I wrote the slides late last night. I might have copied it wrong, but I think it's di, right? Because you need to have like all the bounds on the diameters. I think it's di, but we can talk later about it. Thank you. Right. Okay, so what dimensions are possible? Now we saw dimension 2 is common, but Gwyneth has this nice series of papers from her PhD thesis where he constructs examples of transcendental entire functions with arbitrarily small values of the dimension. So in the entire case, this is between 1 and 2. So the way she constructs these functions is by looking at, so I'm not going to sketch the construction, but so she considers these half strips. You cannot see both at the same time. Okay, in a way that the function outside of strip is small, so it behaves like minus 1 over z, and it gets mapped to some, it becomes in the Fatou set, and the Julia set is trapped in this strip here, where the function behaves like e to the z. And by varying translating these functions by this constant k, she's able to get Julia sets whose Hausdorff dimension has arbitrarily small. Yes.
Clear. I just think to these functions.
Yes. Yeah, I understand. So these functions, I think, so there are several theorems. One of them is about getting arbitrarily small values of the dimension. And then there's another one about actually getting the exact values, which requires to have two bounds, right? Like an upper bound and a lower bound.
The 91 paper doesn't include the 91 paper. So if you can get started to be close to one. And then the latest papers, it's different functions. So you have to, so these functions you can't get.
Right, you cannot find exact values.
Yeah. So you have to get, it's sort of like going between and between the strip and then.
Okay, that's great. Thank you so much. Right. So yeah, that's good. Okay, so until very recently, it was not known if dimension 1 was achievable for transcendental entire functions. And Bishop constructed this example, which is given by, it's a function with multiply connected wandering domain, which has some sort of nice geometrical properties. So the boundaries are really nice and he achieves this Hausdorff dimension equal to 1. Then there is a follow-up construction by Jack and Kirill that also construct functions with, again, with multiply connected wandering domains, but using quasi-conformal surgery instead. If I understand correctly, to this day, the only examples that we have that have Hausdorff dimension 1 always have multiply connected wandering domains. So a question in this area is, can we have other mechanisms to obtain these small Julia sets in the transcendental case? Okay, until here, the rough introduction. So now we're going to focus first on the exponential family, and then there will be another section about the Remenko-Levitz class B. So the exponential family is just this family defined by taking a parameter lambda times e to the z, lambda different from 0. So in the hyperbolic case, there is this very different situation whether there is a cycle, there is an invariant basin of attraction, or there is a cycle of basins of attraction of period p larger than 1. So in the first case, you have a Cantor bouquet, which is this uncountable collection of curves tending to infinity for Julia set. There's a picture in the next slide. So on the left side, you have the Cantor bouquet example. So we have a large invariant Fatou component. So that Fatou set has only one Fatou component, which is this light gray set. Everything else is in the Julia set. And on the right, you have the periodic case with p larger than 1. So the three colors, so in this case, we have a 3-periodic cycle of attracting basins. And so in particular, once you have period p larger than 1, then you have infinitely many Fatou components. Let me see if I wanted to. So in this case, you don't have a Cantor bouquet, but you have what is called a pinch Cantor bouquet, where some of these rays that you had in this case kind of land together, like, for example, here in a repelling fixed point. Okay. So now we're going to focus on the case p equals 1. So when we have this invariant basin of attraction. But before that, we need to talk about the fast escaping set briefly. So in addition to have, maybe I'll remove this part. You think? Sorry. So to define the fast escaping set, so you have your function f, and then on a disk of radius r, you look at what is the maximum modulus of the function f on this disk. So for example, the image of this disk can be something like this. So then you would measure the point that is further away and then draw a circle of the radius m of r. And you can repeat this process infinitely many times. So again, you would now look at the image of the disk of radius m of r, and this would give you another larger disk of radius m squared of r. And you would obtain this partition of the plane into these annuli regions given by iterating the maximum modulus of the function. So this basically tells you what's the fastest speed for the function f that you can go to infinity. So you obviously cannot beat the maximum modulus, but if you start outside of a circle of radius r, then there will be some points which can keep going to infinity in this way, potentially letting some, you might need to, in the beginning, let the point do different things for a certain period of time, but then to be in the fast escaping set, you require that after some point, you keep beating the iterates of the maximum modulus every single time. Right, so this is the fast escaping set of a function f that is a subset of the escaping set. Okay, so the fast escaping set has some, as Phil was saying the other day, some nicer properties than the escaping set itself. One of them is that the components of the fast escaping set are all unbounded. And in fact, in the paper of Mark Mullen, when he computed the dimension of the Julia set in the exponential family, actually the points that he used, they are in the fast escaping set. So these dimensions, it follows from his result that we have that the Hausdorff dimension of the Julia set intersecting the fast escaping set is equal to 2. Okay, so once you have one of these Julia sets that is a Cantor bouquet, you can separate two types of points. You have this uncountable collection of hairs or rays, and each of them comes with a finite endpoint. So you can look at the collection of all the endpoints of the rays and call this end lambda. So Bogusia proved this very surprising result during her PhD thesis, which we now call Karpinska's paradox, which the dimension of the set of endpoints is equal to 2. However, the dimension of the hairs without the endpoints only has Hausdorff dimension 1. So the dimension sits in the set of endpoints rather than the hairs themselves. I put a small sketch of how to prove this. So you first consider these sets. So these look like parabolas. And you look at, so you consider these parabolas which depend on two parameters, P and C. And then you look at the set of points which enter the parabolas for all sufficiently large values of n. And my understanding is that she proved that, so she computes the dimension of the sets which enter this parabola. And this dimension is bounded by 1 plus 1 over p. And then the other part is to show that the Julia set minus the endpoints, so the points that are on the rays, are contained in this, they enter these parabolas. So, which have Hausdorff dimension bounded by this. So when you iterate the points that are not endpoints, they will get into these parabolas for larger and larger values of p. So you will obtain that the dimension of the set is bounded by 1. Any questions about this? No. Okay. Right, so this is a picture from Dirk about this paradox. I don't know if it helps. So I think the idea between this picture is that if you start with a set from the left side, and then you take pre-images, it might be that it's trying to show that the bigger area sits around the areas where the endpoints lie rather than on the rays itself. So when you take further and further pre-images, this area where the rays are becomes very, very thin, and the parts where the endpoints are have larger intersections. So maybe it helps to understand what is happening. Okay, so we talked a bit about escaping points. So if you look at points that have bounded orbit, so we have this inequality. So points with bounded orbit in the Julia set. I should say, let me go back. So here, what type of points do we have? Light gray are points that are in a basin of attraction. So there is an attracting fixed point around here. And every gray point gets attracted to it. Then we have the rays, which we said that they are in the fast escaping set. So what is left is just the set of endpoints of the rays. So every other type of behavior happens in this set of endpoints. So for example, all periodic points are endpoints. All points with Bungy orbits are endpoints. There are also fast escaping endpoints, of course. And there are also all other rates of escape. So you can have slow escaping points. There is a collection of names of moderately fast escaping. Yeah, there are many other rates of escape that they are all sitting within these endpoints. Only the fast escaping ones are in the rates themselves. Let's go back. So now with this in mind, there's a subset of these endpoints that have bounded points of bounded orbit. have Hausdorff dimension strictly larger than 1 and less than 2. And then if you also include, so these are either bounded orbit or Bungee points, it's still less than 2. So, yes? Yes, this is the radial Julia set, yeah. This one is the radial Julia set. So all these two sets, so bounded orbits and Bungee orbits, have dimensions strictly less than 2, so the dimension for these functions is supported on the set of endpoints that are escaping, right? So this is the set that is giving dimension 2. Everything else has dimension strictly less than 2. I'll remind this fact later on. I just wanted to show, so it's also, people have looked at not only fast escaping points, of course, but points that escape slowly. So there's this paper by Dave Sixsmith about slow escaping points in the exponential family. And he shows that this set of uniformly slowly escaping points have Hausdorff dimension 1. So this, basically, if you look here, you see that the rate is given by this iterated, kind of geometric rate. And I think if you drop this one, then you get just this greater or equal than 1. Okay, so now we're going to move to a wider class of functions. So the Riemann-Kolyevich class consists of transcendental entire functions whose singular set is bounded. So we need to include asymptotic values, critical values, and the accumulations of these points. So we consider two classes. So the class B is when this set of singular values is bounded, but potentially infinite. And then we have the class S, which is where the set of singular values is finite. In terms of the dimensions, Gwyneth's proved that in the class B, you have Hausdorff dimension strictly greater than 1 always. And she showed that you can attain all values from 1 to 2. If you have other conditions, such as having finite order or some control on how the function grows, I didn't want to put the very detailed results, then under this kind of mild assumptions, you get that the Hausdorff dimension is equal to 2. What about in the class S? So Chris Bishop and Simon Albrecht proved that this infimum of 1 is attainable also in the class S. So you can find, they use quasi-conformal folding to obtain functions with dimensions which tend to 1 within the class S. And this is the, if you know how quasi-conformal folding works, this is the graph that they use to construct these functions. If you don't know about it, don't worry. Right. This is a small detour about packing dimensions. So Phil and Gwyneth proved that in the class B, you get packing dimension equal to 2. So in this diagram here, which was done by Jack from his thesis, you can see how the combination of Hausdorff and packing dimension looks like. So let's see. So this line here, this corresponds to the class B results. So you have always packing dimension equal to 2. And then from Gwyneth's result, you get Hausdorff dimension strictly greater than 2 and up to, greater than 1 up to 2 including 2. So these are Gwyneth's results. Then Jack proved the points that are on the diagonal. He constructed functions which have packing and Hausdorff dimension between 1 and 2, and these two values are arbitrarily close to each other. That's why he put this kind of blurry line here. So we don't know exactly if they sit in the diagonal, but, well, they need to sit above the diagonal for sure, but we don't know if they are exactly on the diagonal. And this corner here is Bishop's example of the wandering domain. And I guess also Jack and Kirill's example is here. My understanding is that this is still the current situation. I don't know if there has been any progress in filling in this triangle any further. And of course, this result from Jack is outside of the class B. Only this top line is the situation in the. So about the class B, we know as much as we can hope to know. But outside the class B, we don't know much about the combination between packing and Hausdorff dimensions. Okay, so what about escaping sets? So for the class B, we don't have escaping wandering domains and we don't have Baker domains. So every escaping point is in the Julia set. This result from Phil and Gwyneth said that you always contain continua in the escaping set intersection the Julia set for just the general function. So you always have that the dimension of the escaping set is at least 1. And then Gwyneth and Lasse showed that you can get every possible value between 1 and 2 for the escaping. The dimension of the escaping set can be, in the class B, can be take any value between 1 and 2. And you can also have it so that the dimension of the Julia set equals the dimension of the escaping set, provided that you don't take D equals 1, of course, because you always need to be strictly bigger than 1 for the dimension of the Julia set. So Walter and Jorn Peter proved also that if you look at points that are escaping but not fast escaping, you can prescribe the rate of escape by giving some sequence. In this case, you get that these escaping points, like slowly escaping points, have Hausdorff dimension greater or equal than 1. Okay, so I'm just trying to give you some flavor about what type of problems people have been working on. I realize it's a lot of theorems to take on, but I just want to give some flavor about kind of results in transcendental dynamics and what type of things people prove. So about other results in the class B, you can have, so if you look at the set of points with bounded orbit, it has dimensions strictly larger than 1. So for this one, I think you construct what's called like an expanding Cantor repeller, this type of set. Okay, this is the final part of the talk. So until very recently, I think people look at dimensions of the whole Julia set or the whole escaping set. But one other possible direction is to look at boundaries of a 2 component. So if you look at one particular F2 component, what are the possible dimensions in the boundaries? And also this partition between escaping, non-escaping, bungee points, how do they look when restricted to a boundary of a F2 component, right? Okay, so for example, you could have a basin of attraction, right, that is unbounded, and you can have points in the boundary that escape. So the points in the F2 component have bounded orbit, but the points in the boundary could be escaping, even if the component is invariant. So yeah. Right, so I don't need to spend too much time on this slide because Jasmine did an amazing job yesterday. We have our F2 classification, and also we know what basins of attraction are. Right, so there is this theorem by Anas Dunik that is very famous and says that for the polynomial case, if you have an invariant basin of attraction, there is this dichotomy. Either the boundary is an analytic curve, or the Hausdorff dimension of the boundary is strictly larger than 1, right? And in the first case of being an analytic curve, this boils down to 2 situations. So either you have a power map and you have that the Julia set is a circle, or you have a Chebyshev polynomial and your Julia set is an arc of a circle or an interval. And these are the only 2 Julia sets that you can draw by hand. And then Hamilton asked, I think in Hyman's list of problems, whether for entire functions you will always have dimension strictly larger than 1 unless you have one of these 2 cases. I think the question was phrased for general entire functions, so it includes this these two cases. Of course, Baker's result also applies to one single Fatou component, so you still get that for every Fatou component, its boundary contains non-degenerate continua, so the boundary of a Fatou component will always have Hausdorff dimension greater or equal to 1. And there are several cases where the dimension equals 1 is attained. One of them is Ziegel disk with smooth boundary from Avila. The second one is the example we said from Chris Bishop. So all these multiply connected wandering domains have boundaries with dimension 1, of course, because it needs to be greater or equal than 1, and and less than or equal than 1. A third example was by Luca, right? You can construct simply connected wandering domains with almost any kind of boundary that you want. So in particular, you can make them to have, so I think his initial motivation was to make one that was a circle, that was a disk. So that one in particular has Hausdorff dimension 1. The question is, if you have a transcendental entire function, and then you look at basins of attraction or parabolic basins, is it true that the Hausdorff dimension is always strictly greater than 1? Right, so now we're going to look at dimensions of subsets of boundaries. So if you go back at the exponential family, right? In the exponential family, we said that for p equals 1, there is just one Fatou component. So all these subsets that we talked about, the Julia sets, are also subsets of the boundary of this one Fatou component, right? So the boundary of u is equal to the Julia set of the function. So in particular, this Fatou component has a boundary of Hausdorff dimension 2. And the question is, what happens when you take p greater than 1? So if you have this cycle of Fatou components, cycle of basins of attraction, what happens with the dimensions in the boundary of the Fatou component? So one result by Krzysztof, Borussia, and Anna from 2010 is that you have that the dimension of the boundary in this exponential case with p greater than 1 is going to be always between 1 and 2. And if you remember from Macmullen, the dimension of the whole Julia set is equal to 2. So this means that the dimension does not sit on the, is not supported in the boundaries of the Fatou components themselves, but rather, because if you take preimages, you will have the same dimensions in the boundaries. So the boundaries are not on, the dimension 2 points are not on boundaries of Fatou components, but they are rather on this set of buried points. So buried points are points of the Julia set that are not in any boundary of a Fatou component. So they are in the accumulations of sequences of Fatou components, but they don't sit in the boundary of just one single Fatou component. So these buried points are the ones carrying the dimension in the case p greater than 1. What about escaping points in the boundary? So again, from Macmullen, we know that escaping points in the boundary of u for p equals 1 has dimension 2. So what about p greater than 1? So there's this really nice paper from Krzysztof, Borussia, and Anna from 2010, which says that we have this inequality here. So again, we said the dimension of the boundary is less than between 1 and 2. And then the non-escaping points, so these are bounded orbit and bungee points, have the same dimension as the boundary. And bounded orbit points are possibly smaller or equal to this. And the escaping ones have dimension 1. Now I realize this is a lot of information to take into account. So I made a summary. Let's see. So this is case p equals 1, and this is case p greater than 1. So for p equals 1, the dimension of the boundary, this should be the boundary, sorry. The dimension of the boundary is 2, so the dimension sits in the boundary. The escaping points have the maximal dimension, and all the other points are smaller. All the other sets of points that are not escaping are smaller. However, when you switch to p greater than 1, the boundary of the photo component, this is the boundary, is smaller than the dimension of the Julia set. This is one difference. The second difference is where the role that escaping points play. So in the case p equals 1, escaping points have the full Hausdorff dimension, while for the case p greater than 1, escaping points have only dimension 1. So there is this kind of stark dichotomy between one case and the other one. So in this case here, the dimension of the boundary is carried by non-escaping points. So Bungee points or bounded orbit points. Okay? Any questions about this? Yes. So I think when you take, so if you look here like for a right half plane and look at the preimages for right half plane, this set is going to be like much, much smaller because you have, so here you have infinitely many other Fatou components. And yeah, so it's like a counting argument, but you look at sequences like needing sequences of which of these preimages you're visiting, and the set is much, much smaller because you have all these infinitely many components in between. Like all these components here go into the strip, right? So Fatou components need to become much, much thinner when you go here. So when you do the counting with boxes, yeah, I can, yeah, maybe let's leave it at here for now. Right. Any other questions?
But it's actually particularly that also have the dimension 6 and then other stating points. So
Okay, I didn't know that. Right, thank you. Right. So there is this, so this looks technical, but let's just say, so this is a generalization. So the paper of Krzysztof Bogusz-Anana from 2010, it had these two parts. So Bergweiler and Ding generalized this part here to more general functions in the class B to show that some boundaries of basins of attraction intersecting the escaping set have still Hausdorff dimension 1 for a more general class of functions in the class S. So we studied the other part of the result. So there will be a talk by Bogusia on week 3. I didn't want to put the theorem in the slides because you can go to her talk and she will tell you all about it. So we looked at this question when, if you have a basin of attraction or a parabolic basin of some class of functions within class B, what can we say about the dimensions of these boundaries? When is it true that they will always be strictly larger than 1? Is it not? Which conditions play a role into this? So there are several cases, and I encourage you strongly to go to Bogusia's talk. I put only one other picture. So this picture here is one of the functions we consider. So you can think of whether this boundary looks to you like having Hausdorff dimension 1 or Hausdorff dimension greater than 1. If you're not sure, then go to Bogusia's talk. Thank you so much.
Thank you. Are there any questions?
What major domains is something new?
So I don't know about it. I'm not sure that anyone has looked at dimensions of boundaries. I think if someone asked me this question, I would come to ask it to you. So I assume that if you don't know the answer, it probably means no one has looked at it.
Yeah, tell us the answer.
I mean, briefly speaking, there are these pictures here represent 3 different cases. So these are 2 types of unbounded basins of attraction, one with infinite degree and one with finite degree. Like the restriction of the function to the photo component has finite degree, infinite degree, or a bounded case. And we can prove the result, meaning there's some particular class of function for which we can show that in the first case, like unbounded, infinite degree, and the last case, bounded, we can show this, but we still don't know about the middle one. And of course, you can always generalize the conditions that we have in the class of functions. But
Is there a paper?
Yeah.
Distinctive.
Yeah, in the Journal of Dynamics.
But just in general, this kind of proofs, when you prove that something is bigger than one, you actually have a lower bound, like something we construct some sequence of open sets, or it's more like if the dimension is one, you get some contradiction because the homological equation or something.
in this one, we use the similar technique as they did for the paper about the exponential family, about constructing this Cantor repeller and looking at the dimension of that. But it's much more, significantly more technical than their construction. Yeah, and this one is easier. So this one comes together from putting some older results from Brolin and adapting an Azarina as well.
So you do get a lower bound?
I'm not sure. I'm not sure. You should ask Bhushan next week.
There's no more questions. Just say it again.